on. Today we're going to start chapter number 9, and in this chapter we talk about life and evolution of stars. We will cover in the first part masses of stars, binary stars. We'll explain what they are. Then the second part, variable stars. The third part is spectral types of stars. And then we HR diagram. And then we have the source of stellar energy. And we end up with a life story of a star. So we'll start with the first part here, which is binary masses of binary stars. You know the meaning of word binary. Binary, that means 2. And we say here in the top of the slide, more than 50% of all stars in our Milky Way are not single stars. They belong to binaries, which means 2 stars that actually in a system. So what you see here, we have a star A, and then we have a star B. It's a system of 2 stars. Now everything moves, nothing is stationary. So when we talked about the solar system, we said the planets orbit the sun. So if we have a system like this, which star is going to orbit the other star? So in this case, we'll say that both stars will find a common center of mass, and they will orbit around this common center of mass. That means it's not one star orbiting above the other star, but they're actually orbiting around a center of mass. Things always move around a center of mass. So when we look at our own Milky Way, we find a huge number of stars that are basically binary stars. It's a system of stars, and sometimes multiple, of stars. So we have to look at the motion of these stars to understand their orbital motion, and then maybe estimate their masses. So how do we actually look at the center of mass? Now, you're all familiar with the seesaw. So let's look at a case here where you have a fulcrum, and then you have a beam, and it's supported exactly from the middle. Now, you put 2 equal masses at the same equal radius from there. Now, this can be balanced out if the radius, that means the distance between the star A to the center of the mass and star B to the center of the mass. In this case, it's exactly in the middle, and both of them are equal. And the motion here is around the center of mass. What happens if I change this one with a bigger mass? Well, right away, it's going to, due to gravity, it will come down. However, I can balance both of them. If I bring the bigger mass closer to the fulcrum, or the center of mass. And this has to do with something that we call a torque. So in this case here, gravity is trying to bring the mass down, and gravity here is trying to bring this mass down, but this is further. So the force of gravity here multiplied by this distance, it's going to equal the force of gravity multiplied by this distance here. So with this torque, they basically can be balanced out. And in this case, we say that the center of the mass is closer to the bigger mass. So that's what we mean by a center of mass. When the two masses are equal, the center is exactly in midway between both of them. If they're not equal, the center of the mass shifts toward the massive star. So that's basically when you have a binary star, they will be basically moving around their center of mass. So if we can look at this binary system, we know how far where the center of mass is and how far each one from the center of mass. We can say something about their masses and so on. So now, what are the types of the binaries? And here we say that we have visual binaries, spectroscopic binaries, and eclipsing binaries. All of these types of binaries are maybe could be the same, but the technique that we use to decide what we're looking at is a binary star. Visually, that means we're seeing them visually. And spectroscopic, that means we use a technique based on spectroscopy to decide that they are binaries. And eclipsing, it's basically an eclipsing effect that we use to decide that what we're looking at is a binary star. So what are visual binaries? Visual binaries, the idea is you can basically see the system that you look at as two separate stars. And in this case that we are basically looking at here, we have a case where you can see here a small star and a bigger one. Now, in time, when we look at that, you can see that this is in 1960, and how the two stars are oriented to one another. Then this is 1970. So you see, they actually have a change locations. This is 1980, and this is 1990. So from this motion, we can basically determine where the center of mass is. And the center of mass, of course, will be closer to the bigger one. In our case, this is Series A, and the other one is Series B. And Series is basically a bright star that you can see in the night sky sometimes. So ideally, we'd like to see this situation here, where we see a binary star. We call these visual binaries. We can see them visually. And that's the case of Series A and Series B. Series B here we call a white dwarf. So it is not really a star, it's the remaining of a star. So this is basically a visual image here. That's how they are orbiting from observation over time. And from this, we can determine where is the center of mass. And if we know the center of mass and we know their orbital speeds and so on, we can say something about their masses and their orbital speeds as well. So now, there is another technique which we call spectroscopic binaries. So these are not visual. So we cannot see them visually. But what we can do is we can use spectroscopy to learn that what we are looking at is a binary star. So the separation between both of them is A, for example, here cannot be measured directly because the stars are close to each other. So from our range here, we cannot really decide, okay, on this binary system. So a limit on the separation, and thus the masses can be inferred in most common cases. And this is what we call spectroscopic binaries. So how do we do that? Okay. Now, you in schools, they told you that when you look at an atom, the atom has a nucleus, and inside this nucleus you have a protons and a neutrons, and then you basically have a cloud of electrons. But in most of the textbooks, they give you this as orbits. It's one way of explaining that. And they give you the electrons that are basically in these orbits. And they tell you that these electrons, they must have a specific energy to be in this orbit. Now, there could be another orbit further, and the electrons can go to this orbit if they absorb exactly the same amount of energy to go up. So we can excite atoms by giving them this energy. So if you heat them up, or they are subjected to a certain wavelength of light, they can jump from one orbit to the next. And of course, when they fall down, they will emit an energy. This is what we call absorption. So when you have a gas and then you send in light onto this gas, and you try to look at the spectrum, you can see some lines missing, and these lines has been absorbed because of what? Because of electrons. It's taken that energy, it's absorbed, and it's moving to a higher energy level. So we usually try to do spectroscopy. That means we look at the light that we see from the star, and we want to see what colors are there, what is missing, and so on. So that's a technique that we use into that. So now you usually look at the blue and red. So I think I told you in chapter number 6 about the Doppler shift, and I told you when the star is approaching, the wavelength will come toward short wavelengths, and we call that blue shift. And when the star is receding, moving away, then you are basically seeing something that we call red shift, because it's shifting toward longer wavelength. So if you have a binary system here, which we cannot see visually, but we can look at the light that comes from them. Now we look, for example, at the, as we say here, red shift, that means going toward higher wavelengths, and we say blue shift here, that means going toward shorter wavelength. And on the top here, we say receding, and here it's approaching. So when it's approaching you, the wavelength seems to be shorter, and that's why we told it's a blue shift. And when it's moving away from you, we said that this is a red shift. Now, the binary star, they are basically moving around a common center of mass. So if you look at these two lines in the spectrum, and this is line coming from A, this line is coming from B. Now, when the stars basically, one star is approaching, another one is receding away. Now, these two lines, they actually start getting closer to one another. Now, when they are basically from our view here, they line up that way. These two lines are basically come on top of one another. And then as they start orbiting the center of mass, they will be moving away, and we see a separation on these lines here. So we rely on the spectrum that we get, and from that we measure the Doppler shift. I told you when something is approaching, the wavelength will get smaller, and when it is moving away, the wavelength will move toward longer wavelength. So we're going to look at that shift, and we told you that it's the Doppler shift. And I told you in previous lectures that that's the basic idea of how you get speeding tickets. When your car is approaching the radar or receding away from the radar, it doesn't matter. It can always get the Doppler shift and decides on your speed. And that, of course, will give measurement of radial velocities, and we talked about that when we talked about exoplanets and how we can look for a wobble. Now, from this one, we can estimate the separation between the two stars, and once we know that, we can basically get an estimate of the masses. So when the binary system cannot be seen visually, we may rely on this spectroscopy to look at Doppler shifts, and then we can basically decide on their orbital motion and so on. So for example, you see in this cartoon here, that's the primary star, and that's the secondary star. And as you can see here, we put red color when the star is receding, that's mean moving away. We'll see a shift to a higher wavelength, and we call that red shift. And when they are basically approaching, we see what we call a blue shift. Okay, and of course, when they combine with each other, that's why the colors will combine. Okay, that's what saying it should be white here, but this is what we look at. So if we see this separation in the spectrum is moving that way, then we can basically decide that what we have is a binary system. So you can see two stars are lining up from our side here, line of sight. So from our line of sight, they are basically lining up. That's in the red, that's in the blue. So, and then they start basically moving away, and that will start separating from line of view here, and then we see these lines are separate now. And then they will move around and they come back, and that basically from this we know that the binary system is moving, and we can see that in the blue or in the red. Okay, and with this spectroscopic technique we can decide on the separation, and once we know separation, then we can say something about their masses. That's another way here where you look at the intensity of the lines, and you can see if they are in the same line of sight, they will be on top of one another. As soon as they start moving away, you see a separation, and then they come back and they continue like this. Okay. Now you want to basically record this. Now in the old days, that's basically a film. So you look at the spectrum and you try to record it. And from this recording, you can basically decide that what you are looking at is a binary system. Of course, now we can digitize that and we have more technique, but I'm just showing you two other techniques that are used before as well. So if the separation between the two stars for us here that we cannot measure or detect visually, then we can rely on spectroscopy, and we call that spectroscopic binaries. So that's how they could be, by the way, the same binary star. I mean, hypothetically speaking, but they're further away. So I cannot see them visually, and I have to rely on looking at the spectrum or the light that comes from them. And I decide that this is a spectroscopic binary. Now, the other type, we call them eclipsing binaries. And you know what eclipsing is? That means one is dimming the other star, like when we talked about lunar eclipse and solar eclipse. So as you see here in the cartoon, you have a bigger star, smaller star. They will be basically orbiting their center of mass. Now, if they are in our line of sight, that means we can measure their intensity, and we will see this effect where one star can eclipse the other one. So this is an edge on here where you can see. So one star is in front of the other one. The area of this star will cover an area of the bigger star. So when I measure the intensity, I will get the intensity minus the area that's covered by this one. And when this one goes behind the bigger star, of course, I will lose the intensity from that one. And I also will have an effect in the intensity. So as you can see in this cartoon here, you have two binary star. So you have the bigger star and the smaller star, and you want to measure the intensity that you receive from these two stars. So the intensity, you're measuring the intensity from this star, and you get this value here. Now, as soon as this star become in front from our view, or transit between us and the bigger star, it will cover an area of the bigger star. And if it covers this area, then the intensity that we receive from that area is we lose it. So that will give us a decrease in the intensity from the initial intensity that we measure for both stars. And it will continue till the star basically now is not in front of the other star. And the intensity will go back. So you're measuring the intensity of both stars. And then as it moves, and now it's behind the bigger star, well, there will be a decrease in the intensity because you're only measuring the intensity of the bigger star and the smaller star. That's it, you lose that. And it will continue like that till it comes back there and you see another dip in the intensity. So when we see this double dip in the light curve that we get from the star, then we say, well, in this case, we have an eclipsing effect and we have a binary star. So in this case, an example that what we call BW sapphires, and you can see this double dip in the intensity as a function of time. So you know the time as well, and that can tell you that what you are looking at is basically a binary star. This is Algol in the constellation of Perseus. You have two stars, then you have one dip and the second dip, and it continues like that. And that it will give you the period in days. So you can see this is day 0, that's probably day 3 or close to day 3. So you can decide on the period of this. And once you know that, okay, you can basically try to get some information about the size of the orbit and the separation and then masses and so on. So it could be something like a simulation. That's what you get when one star is covering another one. You get a dip, and then basically you get the second dip, and that's basically how you look at a light curve here. In chapter number 6, we talked about transient light curve, but that was the planet. It has no intensity. It's only the star, and we see a decrease in the intensity of the star. And we decided that we have an exoplanet there, and from that also we can decide on the size of the planet and so on. In this case, that's actually stars, and stars produce light. So we see a double dip in the light curve, and that basically will give us what will give us the effect, and we see that we have a binary star. So astronomers, when they make their observation and they look at stars, they try to look at the intensity, variation in intensities. They analyze the light to see the spectrum of that and what varies, and we'll talk later about classification of stars. So all of these are basically done. So in the case of binaries, sometimes they're further away from us that we cannot really measure their brightness. So what we rely on, basically we rely on the either spectroscopic or binaries. And that's why we call them either visual binaries or spectroscopic binaries or eclipsing binaries, depending on the technique that we use in observing them. Is this clear? Then we have another type of stars that we call variable stars. By the way, that's binary. In our case, the sun is a single star. But of course, it has planets orbiting. So we have single stars, we have binary stars, okay. Variable stars, okay, is a star that lost its hydrostatic equilibrium. And you know what a static is, okay? So stars usually, when you look at stars, the stars usually have an effect of gravity that is trying to pull everything in, and the star pressure outward. And in the case of the sun, in chapter number 8, when we talked about the nuclear fusion, and the energy that's produced is pushing out, and in that we told it to resist the gravity. So when these two are in equilibrium, we say that the star is in hydrostatic equilibrium. But what happens if the star loses this hydrostatic equilibrium? Then in that case, it's going to vary over time. And that's when we talk about variable stars. Now, we have two types of variable stars. We have pulsating stars, and we have exploding stars. So pulsating stars, like neutron stars, and we'll talk about the neutron stars, which basically can give you a pulse every a couple of seconds, because it's spinning very fast, and the axis of rotation of the neutron star is not the same axis of rotation as the magnetic field, and that's why you get these pulses. We have what we call RR Lyra, which will give you a day, and Cepheid variables, which is 1 to 60 days. And that's what we call pulsating stars. Now, we have exploding stars, and that's basically when they show extreme brightness. And that will happen in a nova or a supernova, and that's basically toward the end of a life of star. And there is a stage what we call T Tauri, And we'll talk about that when we talk about the way when star comes into existence. So when we look at stars, okay, we have to decide, is the star that we are looking at is a single star, is a binary star? Okay, how do we decide that it's a binary star? Well, it depends on the technique that we use. And then there are stars that are variable stars. Okay, are these stars basically pulsating stars that sending pulses, or these stars are we see that they have variation in the brightness, and that signals sometimes that it is about to go through a nova or a supernova. Now, again, just a case where you have a binary star and what a binary star would do. So in here you have what we call a red giant, and then we have a white dwarf. A white dwarf, will explain later that it comes as the result of the death of star, but in this case it became a companion to a bigger star. Now, when this star is going to lose its hydrostatic equilibrium and it's about to end its life, now this white dwarf will work as a center of gravity, and it will accrete material. That means this star is going to burst. It's like a balloon full of water, and then you burst it, and then you get basically a stream of water coming out. That's exactly what's happening here. So the white dwarf will help this star in ending its life. So it will basically start, the material will flow out and it start forming a disk around the white dwarf. We call this accretion disk. You see here we call flow of hydrogen. Now, white dwarfs, they have a limit. They cannot exceed 1.4 solar mass. And once they exceed that, they will basically give what's known as nova outburst, because the star is basically getting this, the white dwarf is exceeding the 1.4, and this is what we call nova, or sometimes we call that supernova type 1A. So that's basically stars. And how can we look at them? And when you have a binary star and one of them is a white dwarf, what would that do in that case? Now, in this part here, how do we classify stars? Now, stars are far away from here. And I told you in chapter number 2, previously, when they looked at stars, the only thing that can be seen quickly is basically the brightness. And that's why in any constellation, the brightest star was given a classification of alpha, then next to it is beta, and so on. But here, how can we really classify stars? So now we look at the spectrum of the star. And I explained this early this lecture. I told you that when you have atoms and they have a nucleus, and around the nucleus you have protons, electrons, and these electrons can absorb energy and they go to a higher energy level. So what we do when we look at the spectrum of the star, then we look at what we call absorption lines. That's what you see here, these lines here. And these lines are missing. That means this energy has been absorbed. And we can decide from the wavelength what is the energy and so on, and we can also decide on the type of the element. So when stars were basically, astronomers do that, they look at the spectrum and they try to measure it, and then they try to gain information from this. So some stars sometimes they give similar uh, spectrum. So in these ones, you can see here that we give M all the way to V here. So we'll explain what these are. And you can see in this, we basically say temperature. So these are basically related to the surface temperature of the star as well. So early on, when astronomers were collecting these spectrum, when they see general features, they give them a certain classification. So the classification was either O or B or A or M or K. So that was a classification that astronomers used to give. Later on, it was discovered that you can actually get the surface temperature from these spectrums. And an O star, the approximate surface temperature is about 40,000 Kelvin. A B star is about 20,000 Kelvin. An A star about 10,000. An F star is 7,500. A G star is 5,500. K star is 4,500. And M star is 3,000 Kelvin. So there is a pattern here. And now these already were given a classification with a letter. Later on, when it was basically, you can measure the surface temperature from this. Now, these have been rearranged in this order here. O, B, A, F, G, K, M. So some may ask, why do you just make it simple A, B, C, D, and so on? Well, I tell you that because initially that was not known. So they were just collecting spectrum and they're given it this classification. Later, when it was able to, they were able to calculate surface temperature from them, that's the classification that we came up with. So you have to remember this order here. So the best way to do that for you is to remember the statement here. Oh, boy, an F grade killed me. No one wants to get an F grade in the course. I think all of you are hoping for an A. Of course, we don't give an O. Okay. So it is, you have to remember this. So for example, when we talked about the sun, and we said that the sun has a surface temperature of 5,800 Kelvin. So the sun now is classified as a G star, because that's what a G star is. And if you remember, when I started chapter number 8, I told you that the sun is classified as a G2 star. So that's, for example, we have it here as a G2 star. Now, there are other things that not important here. When you look at the spectrum of hydrogen, we have something that we call the Palmer lines, and you have other features, things that are involved, and that's why the numbers are given here. So that's how stars are classified. They are classified based on their surface temperature. Remember when we talked about this in chapter number 2, and we talked about alpha, beta, gamma, and we said these are basically has to do with how bright the star is relative to the stars in the same constellation. But now we have something here that we can measure the spectrum of the star and we can measure the surface temperature. And from this surface temperature, we can basically decide on a classification of the star. So now you have to remember this order here. O, boy, and F grade kills me. And that's basically O star is the hottest, and next to it is B, then to it is A, F, G, K, M. Of course, the numbers, we're not going to go into that. Why we give a number to this star or a number of that star, but this is basically how we look at it. So what we have here is different spectrum going from M, which is the coolest, to the hottest. And there are certain features that are seen there in the spectrum of the star. So you may hear this a lot in the news when they say an M star, an O star, a B star, okay, especially when they talk about exoplanets. And they say, well, we found something orbiting an M star is cooler in a zone where it could be comfortable to basically in the habitable zone that life can exist on, so on. So these spectrum now, they enable astronomers to calculate the surface temperature of stars. Not only that, you can learn something about the composition of the star. What is there in the star? So here we can basically look at different gases and we excite them. And after we excite them, we can look at the spectrum that we get from them. And we look at the absorption spectrum. We can do that here. Now, when we look at the spectrum that we get from a star, we start comparing this, okay, to the stars. Yes, the classification is according to temperature. So O, boy, and F grade kills me. The classifications are in accordance to this. So we'll say this is an O star, a B star, an A star, and so on. Some of you, and I made this point clear, why not A, B, C, D? Well, I tell you, we're always trapped in our history. And when these spectrum were collected, it was not that maybe they were not able to classify them in this way. So when they found out that temperature can be calculated, that's when we came up with this classification. I hope this clarifies the question that I see here. Now, when we look at stars and we tell you that the sun is, for example, we see here the sun is 90% hydrogen and 9% helium. How do we know that? No one actually went to the sun and start basically measuring these. But we rely on the spectrum. And we can do that here on Earth. We can look at hydrogen and what spectrum of hydrogen we get. And we can do it for helium. We can do it for other gases. So when we look at the spectrum that we receive from the sun, we can do that. We decide. So for example, and sometimes you may hear that the sun is 90% hydrogen, and you may hear that it's 70% or 71% hydrogen. You should not be confused with this. Now, this is what we call atomically or by the number of atoms, and here which we call by mass. So, for example, a molecule that is essential to our life, which is H2O. It has two hydrogen atoms and one oxygen atom. So now, if I want to do that atomically, I will say that oxygen is 1/3, and that will be probably 33.3% atomically. For hydrogen, I would say it is 2 over 3, which is 66.7%. But let's say I want to do that by mass, which is weight. Well, the atomic mass for hydrogen is 1, and for, probably I should put that in. When you look at hydrogen, they tell you it's 1 and 1. When you look at oxygen, you may get 8 and 16. So these are the atomic masses here. So when you look at molecule of hydrogen here, then when you look at oxygen, you will say it is 16 over 18 because it's 16 plus 2. And that, of course, is going to give you a lower percentage here, a higher percentage. And when you look at hydrogen, it is 2 over 18. So if I want to do it atomically, I will say I have more hydrogen. But if I want to do it by mass, I will basically get a lower percentage here. The reason for this, it is when we came into the Bronze Age, when we start alloying metals. We don't know of the atomic nature. So the way that when alloying metals, you just take certain weights to give you that. And that's what we have for gold. When you, in gold, they will tell you that it is gold 24K. That's a pure gold. When it is 18K, that means 16 parts of this by mass is gold, and 18 parts of it is gold, and the other 6 parts by mass are non other metals to make it a little bit hard, and you continue down the line. So when alloying these basically became based on weight, that's what easier to do. But now we know that compounds basically combine in accordance of the bonding and the number of atoms to each. So now we do things in accordance with the percentage of atoms. And any one of you that goes to hospitals now and they get their readings, either for glucose or cholesterol or anything, they used to give it in grams per liter or something like this. Now they change to millimoles because now they look at it in terms of atoms. Okay. So in the sun, if it's done by atomically, then we'll say it is 91% hydrogen and about 9% helium. But if I want to look at it by weight, then I will say, roughly speaking, it's 71% hydrogen, it's about 27% or 28% helium. So I don't want you to be confused when you hear these two. In one case, it's referred to by mass or by weight, and in the other case is referred to by the number of atoms. And of course, when we talk about nuclear fusion and so on, we look at the atoms. We're not really concerned with the mass itself. Unless later on we said that in the fusion, the difference in mass, that it transformed into energy and so on. So with the spectrum as well, we can basically not only get the temperature, we can get the composition of stars. What is there? So when we look at the sun, we learn of the composition of the sun while we are here. Now you see other elements there, and you can see that they have very small percentages. And I told you about the fusion and so on. So, but it's mostly hydrogen and helium, and the sun is mostly hydrogen now. So it will continue burning its hydrogen, and of course, when it's going to go to helium and try to get helium into carbon, it will become something that we call the red giant, and then it will explode. We'll talk about that later on. So that's when, in regard to composition of stars, we also talked about classification of stars, where you're going to look at their surface temperature. Now, what we're going to look at next is basically HR diagrams. And I'll try to introduce it here, but maybe we'll talk about it in the next lecture. And it is basically due to two scientists, Etzberg and Russell. They made a diagram, and on the y-axis of the diagram, they put luminosity, brightness, and in the x-axis, they put the surface temperature. We always do that, by the way, for humans. If they are underweight, overweight, normal height, very tall, very short, we can basically do statistics like that. So in this case, they said, what can we know about stars? Well, we can look at the surface temperature of the star, and we can also look at the luminosity of the star. And then they start basically plotting this. But one thing that you have to be careful here when we look at this diagram, the luminosity increases as you go along the y-axis, but along the x-axis, you go from the lower to the higher. And like curves that you are used with when you take x and y, so it's increasing that way, it's increasing that way. In this case, it is increasing that way, but it's decreasing that way in terms of temperature. So that's one thing that you have to be careful with. And then they start putting in all of the any star that they have the luminosity for it and the surface temperature for it, they put that on this graph. Now, the luminosity here is measured relative to the luminosity of the sun. So one thing that I want to make sure that you're aware of, whenever you see a symbol like this, that means the mass of the sun. And whenever you see something like this, that means the radius of the sun. And whenever you see something like this, that means the luminosity of the sun. So usually things are measured relative to these. So when we look at our graph here, you see on the y-axis here, it says L divided by L, and you see that symbol. That means the luminosity relative to the luminosity of the sun. And you see the sun here, and you see across the sun here, the luminosity is equal to what? Is equal to 1. Because you're taking the luminosity of sun relative to the sun, it will give you 1. So there are those who have more luminosity than the sun. Of course, there are techniques, because I told you stars are further away, so you actually see them less brighter than the sun, but there are techniques to decide on how bright they are. And below that, of course, you have ones that are less brighter, and of course, on the x-axis, you have the temperature. And they plotted everything. It seems that most stars fall on a curve here, which we call the main sequence. And main sequence here, sometimes abbreviated as MS. And this is when the star is basically living its life in equilibrium. It will be on the main sequence, and you may actually hear this as an MS star. I will take it from here in the next lecture of how we can basically look at different stars. Any questions on this? Any questions? Any questions? Good.